Hi, and welcome to the second of three videos for section 10.6, which is determinants in Cramer's rule. In the first video, we saw how to find a determinant of an n by n matrix. In this video, we're going to look at a couple of special cases. First off, if A is n by n, then A inverse, so relating this back to inverse matrices, A inverse exists if and only if the determinant of A is not equal to 0. So we saw that calculating inverses is a lot of work, a lot of row operations to get that identity matrix on the left. Well, we can tell ahead of time whether or not that inverse even exists by taking the determinant. If the determinant is not 0, then there is no, if the determinant is not 0, then there is no inverse matrix. So let's look at an example. Let's say we want to show that the matrix A, which is 1, 2, 0, 4, 0, 0, 0, 3, 5, 6, 2, 6, 2, 4, 0, 9. So show that this has no inverse. So basically what we want to do is what? Show that the determinant is equal to 0. So if the determinant is equal to 0, this doesn't have an inverse. Now also remember, we can choose whatever row or whatever column we want to do our determinant off of. So obviously with all these zeros in the 3, I'm going to go with this row. That way I get a lot of zeros, everything drops out, and it simplifies my work a little bit. Now, let's remember our plus minus matrix. Plus minus plus, this is going to be a minus, this will be a plus, this will be a minus, this would be a plus. So that when we're figuring out those minors and those cofactors, we know what value gets associated with it. So all of these are going to be what? When I'm at this 0, it's 0 times its minor. Doesn't matter, it's going to be 0. Plus 0 times its minor mean 0. It's going to be 0. Minus 0 times another 0. Plus 3 times what determinant? Well, I'm blocking off that row and the column associated with it. So I get what? 1, 2, 0, 5, 6, 2, 2, 4, 0. So it's 3 times this determinant. Well, again, I need to pick the best column or the best row to work with, which would be what? This guy here, because of all the zeros in that row. So again, based off of my plus minus matrix, I'm always starting with plus, minus, plus. So this is going to be a minus down here. Remember that they alternate from one to the other. So it's going to be a minus 2 there. So if I expand off of that column, it's going to be 3 times this guy. So 3 times, well, this is going to be a 0, that'll be a 0. So I'm only worried about when I have this row and this column, which is what? Minus 2. So 3 times a negative 2 times the determinant of 1, 2, 2, 4. 1, 2, 2, 4. So this determinant, so it's what? 3 times negative 2 times, this determinant is 1 times 4 is 4, minus 2 times 2 is 4. So it's 3 times negative 2 times 0. So this whole thing is equal to 0. Therefore, since the determinant of this matrix is 0, this has no inverse. I don't even need to try to do the identity matrix, because it's not going to get me anywhere. I'll just end up with a row of all zeros somewhere. So that's that there. One thing we can do, so this one was nice, why? Because we had all these zeros to start with, and then we got some more zeros here. Well, we can actually use that to our advantage by doing row or column transformations to simplify a matrix in order to do its determinant. So before, we were only able to do what? Row operations, because we had a system of equations. Well, this one we're not allowed to switch rows or switch columns, but we can do the manipulations. 2 times a row gives me a new row. -3 times some row plus that gives me another new row. So let's look at an example where we can do that. So we want to know, does A, which is 8, 2, -1, -4, 3, 5, -3, 11, 24, 6, 1, -12, and 2, 2, 7, -1. Does this have an inverse? So, does it have an inverse? Well, let's figure out its determinant. If that's not 0, then the answer would be yes, it does have an inverse. I don't have any zeros here, so I try to look around and see, okay, can I do stuff that'll cancel out? Well, if I look at this one here, if I times 8 times -3, that's going to give me a -24. 2 times -3 is a -6, that'll be gone. -4 times -3 is +12, that'll cancel that out. So what I'm going to do here is do row 1 times -3 plus row 3 gives me a new row 3. So if I do that, what do I get? Well, let's leave everything else the same. 2, -1, -4, 3, 5, -3, 11. So when I multiply that, 8 times -3, -24, plus 24 is 0. 2 times -3, -6, plus 6 is 0. -1 times -3 is +3, plus 1 is 4. -4 times -3, +12 minus 12, 0. And then we'll leave the last row alone for that. So, again, my plus minuses. So we have plus, minus, plus, minus, plus, minus. So that means if I'm expanding off of this row because of all the zeros, the only one I have to worry about then is this column to do anything with, and it's a +4. So it's +4 times the determinant of what's left. 8, 2, -4, 3, 5, 11, 2, 2, -1. All right, so now let's look at what we got here. Do we have anything? Well, if I do -4 times 2, now if I do column manipulation, -4 times 2 is -8, that'll cancel. -1 times 2 is -2, that'll cancel. So I'll only have one guy left here. So this really is 4 times. So what I'm going to do here is what? I'm going to do column 3 times 2 plus column 1 gives me a new column 1. So this is the first time we're doing column manipulations. We can do this with determinants, not with regular systems. So don't, if you're doing reduced row echelon form, don't do column manipulation. That's only for our determinants. So if we do this, what do we get? So we have, let's write the others in here too. So 2, -4, 5, 11, 2, -1. So times 2. So -4 times 2, -8 plus 8 is 0. 11 times 2 is 22, plus 3 is 25. 2 times -1, -2 plus 2 is 0. So now I'm going to expand off of this row. So the only one I have to worry about is, or that column rather, so we have that row, and now we need our plus minuses again. So plus, minus. So it's 4 times -25 times the determinant of what's left over. 2, -4, 2, -1. So I get 4 times -25 times 2 times -1 is -2 minus Negative 4 times 2 is negative 8. So I get 4 times negative 25 times negative 2 minus a negative 8 is plus 8, so that's negative 2 plus 8 is 6. So you have 4 times negative 25 times 6 gives you negative 600. So because it's not 0, to be honest, I don't even care what that number is. What I'm concerned with is that it's not 0. Therefore, because it's not 0, this matrix does have an inverse. So you could go through the process then of converting it to the identity matrix on the left side. That would give you the inverse. So that's it. Sort of two special things we're looking at there. Does it have an inverse? And then the idea of column and row manipulation in order to make our work a little bit easier by creating a bunch of zeros. So come on back, we'll look at Cramer's rule, which is going to finish up section 10.6.